All right. So last time we were talking about momentum and collisions, and I just want to make sure, any questions about what we talked about last time? Are we feeling pretty good about how to do the computations, how to figure things out? Why don't you give me a thumbs up? You can either press the thumbs up button, or if you're in video, you can give me a thumbs up. If you're feeling good, thumbs down if you're not. Thanks, Jesus, Bradley, Victor, Ian. All right, cool. We're seeing lots of thumbs up. That's what I like. Again, at any point, please do not hesitate to jump in and ask me a question, either through the chat or through turning off your mic, right? Just hitting the space bar and coming in. Okay, so just to kind of review real quick, momentum, remember it's the product of mass and velocity. So large momentum doesn't necessarily mean large mass or large velocity. It's a combination of the two. And so momentum is also a vector. We also had impulse, and impulse, that was basically the force over time kind of deal. And we saw that there was a form of Newton's second law that now involves momentum, right, instead of just acceleration. And we started using that with collisions. With collisions, I want you to remind you that they're really the two types are elastic and inelastic. So what was the difference? What is elastic? Do you remember? What's an elastic collision? All right, so Victor just put up conservation of energy. Yeah, so with an elastic collision, you don't lose any energy. No mechanical energy goes away in that collision. So whatever you started with is what you have at the end, which is not real, right? In general, collisions we're going to see are not perfectly elastic. Some are pretty close, but for the most part, they're not elastic. We tend to lose a lot of that mechanical energy into other things. Primarily heat and sound. If we have a collision that causes something to break, like you can imagine if we throw like a snowball against the wall and the snowball just splats, a lot of the energy is going into deformation, right? And so, but anyway, so elastic is perfectly elastic, means all of the energy is conserved. Anyway, so inelastic is we lose some energy. And then we can have perfectly inelastic. What was that? Do you remember? Look back in your notes.
Objects bounce back at the same speed, like changing kinetic energy is 0.
Yeah, so, you know, Ralph put in the chat there that the kinetic energy afterwards is 0. So we lose all the kinetic energy. And so it's not quite what Jacob said about coming back at the same amount. Coming back at the same amount is really elastic. That's where we have the same kinetic energy, is going the opposite direction. But yeah, so perfectly inelastic is when our kinetic energy drops to 0. But that doesn't always happen. The other thing that sometimes happens is our particles stick together. Like we saw a bunch of examples with that. But through all these collisions, no matter what, momentum is always conserved. And when it's one-dimensional, it's pretty easy. I do want to remind you that the big thing we have to watch out for is the like left versus right. Remember when we were looking at those, sometimes it's not the difference in the two numbers. We actually have to subtract the negative of the other one. Realize that these are vectors. So direction matters. So sometimes it's more than what you think. And then, of course, if we're in 2 or 3 dimensions, we have to go to the 2 or 3 dimensional vectors. But we just go component by component, just like everything else you've ever done. Momentum's no different, right? Okay, so I think that's pretty much where we were, or where we left off. And are we feeling pretty good about that in general? No issues, thumbs up, thumbs down?
I had a quick question from the homework.
Oh, okay, go for it, Bradley.
I'm going to share my screen because I have it pulled up and it's probably just easier for you to read it.
Okay, I think I have to allow you to share the screen though. Hold on. Oh, no, okay,
Yeah.
I got it. Yep, go for it.
So number 10, it's can objects in the system have momentum while the momentum of the system is 0?
Okay.
So I argued that yes, it's possible, and I thought about it in terms of vectors. So suppose you have two objects moving in opposite, like towards each other, and they have the same momentum, and they hit, and the net total afterwards would be 0 momentum, but they're objects. The system may be 0, but the objects themselves have momentum afterwards. Does that make sense? If they're equal and opposite?
What you just said to me totally makes sense. What I want to turn it around to everybody else is, what do you think? Does that sound reasonable? Because again, the question is, well, let's just think about what Bradley was saying. So we have two objects that are, let's say, coming towards each other. So we'll just use my fists or the two objects. And if they're the same, they can have the same momentum magnitude for sure, right? That the product of their mass and velocity are the same as they're coming in together, but they each have momentum. But if we were to look at the system and we add those together, we would get 0 because those vectors would cancel each other out. So as a system, the two fist system, the momentum is 0, but individually they each have one. So I think you're dead on there, Bradley. I think you're right that it's definitely possible. If we had a system of 20 things that are all kind of whizzing around doing whatever, we could still end up getting a sum total of 0 if we add all the momentum vectors, and yet they all individually have a momentum. So that's a big thing to recognize. And when we talk about conservation laws, it's always of the system, Individual things have whatever energies, whatever momentums, whatever else we're going to be conserving. But we look at the group, whatever the group's total is what we're looking at. So, yep, I think that sounds pretty good. Other questions on the homework? All right, well, like always, I'm going to take no sound as a yes. So what I want to do, I'm going to go ahead and share my screen and see if we can check out this video, because I did find a good video of the baseball hitting the bat. And just to remind you what this was all about, we were talking about impulse, right? Which was force over time. And we saw that large impulse means a large change in momentum. And in the example of a baseball that's being hit, there's an incredible change in momentum because of the fact that as it's coming towards the batter, the momentum vector is pointing that direction, and as it leaves the bat, it points the opposite direction. And you can really see what happens with the impact here. I might have to bounce back here just a little bit. But check out the deformation on that ball, right? It starts nice and round and really compresses. So are you guys able to see that all right? So think about this in the context of energy, right? There's a huge amount of energy that's lost in that compression. In order to deform that ball, there's got to be a huge amount of compression. But even better, I don't know if we're going to be able to see it, the bat itself also gets deformed. They're just showing you that the bat getting snapped. Because what ends up happening is the bat bends. And if it bends enough, and we'll talk about this later, if it bends enough, it goes beyond the amount of stress that it can actually handle and causes it to break. Oh yeah, there it is. Check that out. You can even see that bat kind of like wobbles a bit. We get a little bit of wave action, which, hey, look at that. We're going to talk about waves in a few chapters as well. But these are the kinds of things that happen in collisions that we don't even necessarily notice. But in the physics world, this is what's taking us from elastic to inelastic. It's showing how much of the energy we actually have, what we gain, what we lose. And I think this is one of the reasons why I love sports, honestly, is that there is so much science behind it if you really look at it. Anyway, that's what I meant to show you guys last time. It's from a series called Sports Science. If you're interested in that, you should definitely look some of those up. It was through the Discovery Channel. I think they also had them on ESPN, but you can find them on YouTube. Anyway, so let's continue our discussion because we have a little bit more to talk about with collisions and all that. And what I want to talk about next is what we call the center of mass. So I'm going to go to the whiteboard. And again, I'm just going to be fiddling with my mics so that I'll switch. So there'll be a little bit different sound quality as I switch here. All right, but now you should be able to see the whiteboard, and let's just talk about this. So center of mass is the idea behind this is that when we have a whole bunch of objects, let me just draw a couple of random. Right, so here's object 1 and 2 and 3. Is that there's some place. Oh, and I just realized this looks like a face. Anyway, so there's going to be some spot where we can actually treat this system as a one-point mass. It'd be as if all of this mass was located at this one spot, and it allows us to treat it as that location. Now, I'm not going to show you the derivation of why we can do this because it's really kind of boring, and I know it's in the book, but it's basically if you look at the individuals and you add up all their masses and do all that kind of stuff, you can actually hone in on one location that behaves as if it's the location of all of it at once. So the center of mass, we're going to use X bar and Y bar as our way of denoting that this is the center of mass. So that little bar on top, and I will call it X bar and Y bar, that's our center of mass. If you've taken statistics, you may remember that this is like mean or average. It's the same kind of idea. This is the average X position. All right, so the way that we define these, X bar, what we do is we take the sum of the product of the masses and the positions of the individual objects. And I'll show you some examples so that you can see where this is coming from. But we take that sum. So hopefully you guys are familiar with this kind of notation. Obviously this would be I equals 1 to however many, like in this case it would be 1 to 3. But then we divide that by the total mass. So we actually have to do two different sums. One is get the total mass, and then the other is to take the masses times the x's. Looking at the list, I know Ian has already been through first year calculus, and the rest of you, I think, are in first year calculus right now. Ian, you may remember this as the moments.
Yeah, moments of inertia.
Right, when we did moment of inertia calculations, this was actually the first moment, is this mass times distance. So for the rest of you guys, you should be running into this sometime. Actually, did you see this last quarter?
Yeah.
Yeah, they learned it like right near the end of,
Okay.
or like just before, like what was it?
Okay, that makes sense because it is during the integral stuff. It's been a while since I taught that class. And it comes back again later. But that's all we're doing. We're adding up those first moments. And you may remember that was sort of the balance beam kind of thing. If you want to figure out where people need to be on the teeter-totter, on the seesaw, you would look at their mass and how far away they are from the fulcrum. That's really what this is doing. It's finding that balancing point. Okay, so you actually may have even seen the derivation of this in calculus, but like I said, I don't want to bore you with it. So that's our x bar. That's how we're going to find that. And then if we want to find y bar, it's not going to surprise you that we do exactly the same thing, except instead of x's, we put in y's. So for y bar, we're going to have the sum of the mi y I over the mi. Sorry, just muted myself. I got a bit of a cough. I promise it's not COVID. It's not COVID. It's talking for 5 hours. All right, so let's actually do a calculation here to find the center of mass. So let's take 3 point masses and let's put them on a grid. So let's see, we're going to have one of them over here at -1, 0. Let's call that point A, point mass A. We're going to have point mass B, which is up here at 0, 2. And then we'll go with point mass C. That's over here at 2, -2. Okay, so there are 3 masses, and let's actually give them some mass. Let's say that A is 5 kilograms, B is 1 kilogram, and C is 3 kilograms. So the question is, where could I put a 9 kilogram mass so that it basically is behaving individual masses? Okay, that's what center of mass is really trying to find. All right, so let's use these formulas and let's see if we can find it. So I'm going to have to erase this to get some space, but hopefully you have it written down. But let's start with x bar. So for x bar, what we need to do is we need to take the masses times their x components and add them up. So for A, we've got a mass of 5 kilograms that we're going to multiply by -1 because that's the x component. Then we've got a mass of 1 kilogram for B, and we're going to multiply that by 0 because that's its x component. And then we're going to get 3 times 2 for the third one. And then we want to divide that by the total mass. So I'm going to go ahead and write it out, but really it's just add them up. All right, so we get -5 plus 6 is 1. 5 plus 1 plus 3 is 9. And we get 1 9. All right, now we do the same thing for y. But this time it's going to be 5 times 0, 1 times 2, and 3 times -2. But again, the sum of the masses is still the same, 5 plus 1 plus 3. All right, well, on top, we get 0 plus 2 minus 6, which by my count is -4, and the bottom is still 9. So this gives us -4 nines. So our center of mass is located at 1/9 minus 4 nines, which would be on our graph somewhere right around here, plus or minus. Excuse me. All right, so that's how we find the center of mass. And what's really kind of nice about this, the reason we even care, is that when you have a particle or an object or anything that's moving, if for any reason it falls apart, breaks up, anything like that, even though the individual pieces are going to be moving around doing whatever, they're all going to be moving such that the center of mass continues to do what it did. So a good example would be, let's say we've got something that we're firing up into the air, like a cannonball or something like that, that then breaks apart. So let's say that this is our cannonball. And in the absence of air resistance, of course, we know that it's going to follow a parabola, do something like this. But let's say something happens that causes this to break apart. So maybe we've got an explosive charge in it or something, but it shatters into pieces. Right? As this stuff breaks apart, it's still going to basically follow this path, such that the center of mass is always located on that parabola. So they're flying apart, and yet the center of mass still follows this. So if you're not concerned specifically with the individual pieces, you can follow the center of mass and still know how everything is going. And really what this does is it simplifies calculations a lot. Because instead of having to worry about like these 3 individual pieces and the forces acting on them, calculating the A's and all that to help define the paths, we can instead just do one calculation on the center of mass. And often we know how these things are moving away from the center of mass due to whatever kind of explosion or impact or whatever it is that caused them to break apart. All right, so when you have point charges, or point masses, finding center of mass is not really that big of a deal. Now, here's what's kind of cool is you might have things that are not point masses, but you can still do sort of the same thing. So here's the next example I want to show you. Let's say we want to figure out the center of mass of the Sun-Jupiter system. Okay, so we're going to have the Sun. And then somewhere out here is Jupiter, and you know that it's Jupiter because it's got the great red spot. Right.
Before we even start, I just have a question about
Go for it, Bradley.
that concept. Wouldn't the center of mass be at the focus if these follow elliptical orbits?
So
Sun at one focus anyway?
Hold on a second. I want to look at you when I talk about this part. All right. So in terms of like a planet and the center of mass, we do know that planets follow an elliptical path. And we also know that the sun is located at one of the foci. But the center of mass is not either of those. Like when we talk about the sun is at a focus, it's really the center of mass of the sun that's at the focus. The elliptical path, that's the center of mass of the planet, is traveling that elliptical path. But the center of mass of that system may be somewhere completely different. It totally depends on how the masses relate to each other, how big they are relative to each other, and how far away they are. For example, let's say we have 2 objects that are exactly the same mass. Okay, so there's a second Earth, let's say. So we've got Earth and we've got Earth 2. If they have exactly the same mass, then the center of mass is going to be exactly dead center of those 2. Think of remember the teeter-totter thing?
Yeah.
Think about what's going on there. If we have equal mass people on that teeter-totter, to balance it out, we got to be smack dab in the middle. Now, what if one is bigger than the other, right? So now instead of 2 Earths, we have Earth and we've got the moon. Okay, so my pen cap is the moon and this is the Earth. So now imagine that this is a teeter-totter. If I were to try to go dead center, the Earth is totally going to skew it. So we're going to have to slide that center closer to the Earth, right? Because we need to decrease that first moment of the Earth. So that balancing point is going to drift in this direction. Again, it's not going to be at the focus of the ellipse that the pen is going around, the moon's going around, necessarily. It could be. It absolutely could be, depending upon how the forces balance out, or the masses balance out, but highly unlikely. Highly, highly, highly unlikely.
Okay, that definitely makes sense. So the path is the center of mass for that planet, as is the focus is the center of mass for the sun. And
right.
that
So
makes complete sense.
Yeah, so all that time back in like math classes when we talked about things being at the focus or traveling, we're always talking about what we never said that we should have if we wanted to be good science-wise, is that the sun's center of mass is at one of the foci, and that the center of mass of the orbiting object follows the elliptical path. Depending upon how things are set up, sometimes that's not a distinction you really have to make. Like if we're going to talk about a satellite going around the Earth, since satellites aren't very large, those centers of masses, they're not going to stray very far from any piece of the satellite itself, right? And the same thing kind of happens if we want to talk about the Earth going around the sun. I know we tend to think that the Earth is large, but compared to the sun and to the orbit that the Earth is actually taking, it doesn't really matter what part of the Earth you're talking about. But there are situations where it could matter, right? Like when we start talking about, say, the moon and its orbit around the Earth, now that the size of the moon relative to its orbit is pretty substantial and might be enough that we'd have to worry about it. So anyway, hopefully that makes a little bit more sense.
Absolutely. That was the coolest thing I've learned in 3 weeks.
Yeah, me too.
Woohoo! I'll take it. I'll take it. All right, so let's go back to this and talk about how we can figure out where the center of mass of the Sun-Jupiter system is. But before we actually calculate it, I'm curious, where do you think it is? Do you think it's going to be dead center? Do you think it's going to be closer to the sun? Do you think it's going to be closer to Jupiter? And in fact, I'm going to make a poll here real quick. We're going to see how this works. I've not tried this with Zoom. Oh, no.
Oh, and if you can get it to work, I need to tell Carl how to get it to work because he was trying.
Well, it just popped up. It says you're logged in from another device. So it might be thinking my phone is the primary me. But then it opened up a window. Oh, okay. Oh, here we go. Here we go. So let's see. Type my question here. Where is this? Sorry, just give me 1 second here real quick. All right. I think I figured out how this works. Okay, well, at least it brought me to a page where I could make my poll. So now let's see if I can pull up that poll again. Let's try this. If not, I'll go to my phone. All right, let's see. All right, never mind. We'll try this again some other time. All right. So here's so just type this into your chat box. So here are your three options. Is the center of mass going to be exactly in between Jupiter and the sun, like dead center? Or is it going to be closer to the sun or closer to Jupiter? What do you think?
The sun.
All right, so Ian thinks closer
Yeah,
to the
I'm gonna
sun.
say the sun too.
Bradley says the same. Cesar, Ralph, Victor. Okay, so yep. Okay, it's looking like it's unanimous. We're all thinking it's going to be closer to the sun. So why? Why is it going to be closer to the sun?
It's much bigger mass.
The sun has more mass in the system. So.
Okay, so the sun is much more massive for sure. Okay, so let's run the numbers here on the board and let's see. All right, so the sun, its mass, and I got this from I don't remember what resource I found it, but it was one I trust. It's 1.99 times 10 to the 30 kilograms. So huge, right? 10 to the 30 is incredibly large. Well, Jupiter's no slouch. Jupiter comes in at 1.90 times 10 to the 27. So it might not be as different of a mass as you thought. I mean, yes, the sun is 1,000 times more massive, but only 1,000. Like, that really shows you how large Jupiter is. These are masses that we can't really even comprehend, but you know, they are what they are. All right, so there are their masses. And then the other thing I'm going to tell you is that the orbital distance here, and it's not exactly this because it's not a circle, but it's pretty close, that this R is 7.78 times 10 to the 11 meters. All right. So we want to find the center of mass. So let's use the center of mass formula, but it's going to be pretty easy because we only have two things. But we need x coordinates, y coordinates. So basically what we need to do is create some sort of a system, right? Some sort of coordinate system. And in physics, we are masters of our own coordinate domain, so we can do whatever we want. And so let's be smart about it. So first thing, I just realized I got this off. First thing, let's make this one-dimensional. Let's not bother with 2 dimensions. So let's make it so that our coordinate system is such that they're both on the same axis. Okay. Then we need to choose a place for 0. And it totally doesn't matter. So my recommendation, if at all possible, is put the origin at the center of mass of one of the objects. So I'm going to do exactly what I just did right here, which is I'm going to make my coordinates so that the origin 0, 0 is the center of the sun. The reason you want to do this is because now when you go and you do your calculations, remember what we do is we take mass times the coordinate. If the origin is at one of the centers of mass, then the coordinates for those are going to be 0. 0 times anything is just 0, and you don't have, I mean, it's way less calculation. All right, so we only have an x bar. We don't even have a y bar. So we're going to take their masses times their x's. So just for the sake of doing it, I'll write it out. We're going to have 1.99 times 10 to the 30th times 0, because that's where the sun is. It's at 0 on our coordinate system, which then the next one we add is going to be the 1.9 times 10 to the 27. And we need to multiply that by its distance away, which was that 7.78 times 10 to the 11th. And then we divide by the total mass. So we just take those two masses and add them together. All right. So if you do this, let me just first do sort of a size order of magnitude computation. I don't know if you guys do this very often, but I find this really handy. Let's just look at what the power of 10 is going to be on the top and the bottom. So this first piece is 0. Don't worry about that. But if we look at this product of mass and distance for Jupiter, we have 10 to the 27 times 10 to the 11, which is going to be 10 to the 38, plus or minus a little bit, right? It might be off by 1. It might actually be 10 to the 39 or 36, depending on how the numbers are, but it's right around there. On the bottom, I have 10 to the 30th, 10 to the 27th that I'm adding. Well, the 10 to the 27th doesn't really matter when I add it to 10 to the 30th. That's going to be in this third decimal place. So worst case, it's going to bump this up to 2.00 something times 10 to the 30. So we've got 10 to the 38 divided by 10 to the 30th. So we should get a number around 10 to the 8. All right, well, if we do that, take our 10 to the 8, we're going to get X bar, do the calculations, you get 7.42 times 10 to the 8. So again, it was in that order of magnitude that we expected, but it's around 10 to the 8. All right, so where is that? Well, it really comes down to how large is the sun. And it turns out that the sun, the radius of the sun as a ball, so if we just look at that number right there, it's on the order of 10 to the 8. So it turns out the center of mass is like right outside the sun, just barely outside the sun. So kind of interesting things. If you do the same kind of calculation for other systems, like specifically, if you were to look at the moon and Earth system and do the same thing, it turns out that the center of mass of the Earth-Moon system is inside the Earth. It's still actually inside the Earth. That's how much more massive the Earth is than the moon. But that's also why, if you were to look at the Earth-Moon dynamics, like, let's see if we can just kind of visualize this. So we got the sun and we got the Earth going around the sun, right? And it does, it's not a circle, but we'll call it, right? And then around the Earth, you've got the moon kind of doing the same thing, right? Going around. Well, the Earth and the moon together as a system is going to spin kind of like a barbell, right? So think about a barbell, and it's going to be rotating like that, going around and around and around, except it's not going to be that noticeable, because this kind of what I'm showing you would be where the center of mass is in between them directly. For the Earth-Moon system, that's going to make this be our Earth-Moon barbell, it's going to be rotating about a point very close to the edge. So instead of spinning like a propeller, it's going to be spinning around like that. And what ends up happening because of the moon is that Earth's orbit isn't an ellipse. It kind of wobbles a bit. Let me show you on the whiteboard kind of what I mean. It's going to look, I'm exaggerating it, but it's going to do that kind of thing, where you get these little, I don't know what you want to call them, but little disruptions in the ellipse that are because of this oscillation. And this was one of the things that actually led to the sun-centric, the heliocentric model of the solar system. I don't know if you've looked much into the history of that, But of course, a long time ago, everyone thought that the Earth was the center of the universe. And it makes sense. I mean, you go outside, you see the sun move around us and then come back and do it again. You see the moon do this. You see all the stars do that. And so it was really natural to go, well, of course, everything must go around us because we see it. We literally see it. Not realizing that it's because we're rotating, right? Well, when they first started challenging it, the first reason that anybody even started challenging it was that they were looking at the orbit specifically of Venus, because Venus is super bright. In fact, you can see it, I think, in the morning right now. But Venus is super bright. You can totally see it. And if you do the numbers on it, you see this wobble. You see this, they call it retrograde, because it actually goes the wrong direction. Think about if Venus does this across the sky. This is what it would do if it was going in a circular path. But what they would see is it would come and then go back a little bit and then come back. So every once in a while, there was this blip where it kind of went backwards. Call that retrograde. The reason we see that, as opposed to like with Mars or Jupiter, is because Venus is inside us, closer to the sun. So you can see the same thing with Mercury, just Mercury's harder to see because it's closer to the sun, and we don't see it as often. But anyway, they saw this. And so, of course, they tried to do what everybody tries to do, which is make their model still fit this new thing, right? Because no, we're certain the Earth is the center of the universe. So we're just going to change our model a little bit. So you put in a little tweak. And this is not, I mean, scientists still do this, right? You'll make your hypothesis. Turns out it's not quite right, but you still run with your initial idea and you just tweak it a little bit and try to make it fit. Well, the problem was they kept tweaking and tweaking and tweaking. And the next thing you know, it became super complicated. And it wasn't just as simple as, oh, it's just going around us. So then when it got proposed with Copernicus and Galileo and all that no, it's actually that the sun is the center and we're going in a path around it. The reason they went there is mathematically it was so much simpler. And that's the good old, if you've heard of Occam's razor, that's the simplest explanation, is the most likely one. That's a kind of a philosophical idea. And so they went, no, what makes more sense is that it's actually the sun that's at the center and we just happen to be going around it. Turned out they were right? We now know that that is the case. And it's because of these weird things that they noticed that are due to the fact that they aren't point masses and that we do get these things that are paired together and all that. So anyway, but if we've got a center of mass, it's super nice because you do it. So you guys probably remember then how you find the center of mass of really weird shapes, right? Like what if it's not a point mass? What if we've got some sort of an extended object, right? More of like a continuous object as opposed to a discrete object. Do you remember how we do that?
With an integral.
Yeah, we're going to have to integrate. So if we've got some sort of weird shape, but we do have a density kind of distribution, what we have to do to find the center of mass is basically, all right, well, we put on our coordinates and we break it into little chunks. So you probably saw similar pictures with Larry, right? And you think about, okay, where is this mass relative to the x-axis and the y-axis? And so you would calculate that little mass chunk. So think about what we're doing. Like if we want to find x bar, it was the mass times x. So we're going to have our xi times, I'll call it delta m I, so the little chunk of mass, right? Then divided by the sum of all the dmi's. So we would do that for every single one of the pieces. Well, obviously to make that better, we shrink these things down. We make them infinitesimally small, which means then the sum, we've got an infinite number of them. And the next thing you know, this turns into an integral, right? So we're going to integrate the x dm. And then the bottom, if we add up all those little differential masses, we just get the total mass. So you probably remember doing that. It's a great example of using calculus. And then similarly, y bar, you just exchange the x with a y. Right? So you kind of remember doing that kind of thing? Yeah, maybe, sort of. So we can actually speed up the process sometime by looking at bars that are either horizontal or vertical. Because if all we're really concerned about is distance away from the axis, well, if we're a set distance away from the x-axis, let's say, that's the same y value. And it's the same y all the way across, so we can do a horizontal strip or a vertical strip if we're going to go the other way. So let me just remind you, we'll do an example here. And we'll make the shape not terrible. Let's just look at a semicircle. Okay, so I want to find the center of mass of a semicircular plate. And we'll even give it a radius. Let's say that it's got a radius of A. But I want to find its center of mass. Now, one of them we don't actually have to calculate. Right? Which coordinate do you know? One of them you should know, either the x or the y coordinate for this.
The x.
Why the x? Where is the x, Bradley?
A. I guess no.
Yeah, it would be the center, right? Like the
Okay,
center
so
of the
it's going to be
semicircle.
exactly on the symmetric line. Yeah, so if we think about that vertical line that kind of divides it up, we know that its x coordinate is going to be somewhere on there. So that center of mass is going to be somewhere on this dashed line, just because of the symmetry. Now, we're assuming constant density. If the density isn't constant, we have to worry about that. We have to take that into account, but we're going to go with that this is just constant density. Okay, and then, oh, it looks like Cesar just said slightly towards the bottom in the middle. So on the bottom half, what do you guys think? Does that sound about right?
Yeah, that sounds about right to me.
Yeah. Why? I agree. It makes sense. But why do you guys think that that works?
There's more area along the inside of the bottom half, and therefore more mass.
Yeah, that's exactly it. You can kind of think of it if you think that seesaw kind of stuff. There's more weight on this side of the seesaw on the bottom side. So we're going to have to slide that center of mass down. So I don't know exactly where it's going to be, like on the picture here. We'll calculate it, but I agree it's going to have to be somewhere on the lower half, but exactly middle, left to right. Okay, so let's actually do the calculations and figure out where it is. All right, well, let's start with the mass, right? Since this is constant density, to get the mass, we just need to know the area and then multiply it by that density. So let's just say we're going with the density of rho. So constant rho. And I'm also going to put some coordinates on. Let's go ahead and put coordinates here so that we're going right down the middle. This way we know that our x bar is equal to 0. I'll show you how that still gets calculated when we actually run it with this function, but we already know that. So the real question is, what about y bar? All right, well, we got to get the mass. So the mass is going to be the area times the density. The area of this thing, since it's a semicircle, it's going to be 1/2 pi r squared. So we'll put the a in there, and then times rho. So there's the mass of this thing. Let me write that up here. Conserve space. I think that's one thing I'm going to learn from this experience is how to maximize the space on the board. Because when I'm in class, I've got a huge board. I can write all over the place. Here, I'm like, oh, I got to really conserve it. I think that might be a new conservation law. Conservation of space.
Conservation of ink.
Ba-dum-bum. Hey, it's good to know that things
Conservation
don't
of
change,
whiteboard
even though like
exposure.
I'm at home and you guys are over there, right? Okay, so there's our mass. So now let's get our X bar and our Y bar. So let's start with the X bar. So for the X bar, we really want to do kind of like chunks that are the same distance away in the X direction, which is going to be like a little strip like this. So think about that strip. So it's got a thickness of dx. It's a distance away of a generic x. And so what we're doing is we want distance times mass. Well, the mass of that is basically going to be found the same way, which is find its area times its density. Okay, well, in order to do that, we're going to have to figure out how high that is. But that's just going to come from the formula for this. It's a semicircle, so we know that y is equal to the square root of a squared minus x squared. You solve for the circle. So the height of that is square root of a squared minus x squared. Its width is dx. So the area is going to be the square root of a squared minus x squared times dx. We need to take that area and multiply by the density. So that gives us our mass. And remember, what we're looking for is mass times distance away. So we're going to put in an x. So x bar, we're going to find by integrating this. So let me just again break down what all the different pieces are. This was our distance away. We always have distance away times mass. This remaining bit is our mass. It's density times area. This area is the height. Right? The height of this is the y, square root of a squared minus x squared, times its width. And then, of course, we need to do the bounds, which are just going to be from minus a to a, because we want all those little vertical strips. All right, so we take this, and then we have to divide by the mass. So we'll divide by 1/2 pi a squared rho. So go back and look at the formula for when it was point masses, and you saw that the top was the sum of xi mi. Well, that's what this is. Remember, an integral is a sum. It's just an infinite sum. And then we divided by the total mass. And that's where that 1/2 pi a squared rho is. All right, well, you do this. You actually do this calculation, and you do get the big fat 0. And it's because we're going from minus a to a. This is an odd function, so they end up canceling. All right, but if we want to do y bar, it's going to be similar. We're still going to go from, well, let's not put bounds on yet. For sure, I know we're still going to divide by the same mass, the 1/2 pi a squared rho. But now let's build our bit on top. This time we're going to go with horizontal strips, because a horizontal strip holds all the points that are the same distance away from the x-axis. So we're going to be some distance y away, right? And then we're going to have a thickness of dy. So let's start building this. we're a distance y away. Our mass, we have to take density times area. So the area, we need to get the height of this times its thickness. Well, I'll leave a spot for the height, but the thickness we know is going to be dy. So now, if we want to get the height of that, we want to do kind of the same thing, except instead of using a function of y equals, we want to use x equals. Because this side right here is x equals the square root of a squared minus y squared. Hopefully you remember in calculus, whenever you're just turning yourself sideways, you basically just replace x's with y's, right? So we're doing the same kind of thing. But this isn't going to be the height, because that's only this right-hand side. So the square root of a squared minus y squared is only this part of the strip. In order to get the whole thing, I got to double it. So I'm actually going to get here 2 square root of a squared minus y squared. But exactly the same idea. Area, so height times width, times density to get mass, times distance away. And now we need to put bounds on y. And this one, we're actually going from y equals 0 up to y equals a. So instead of like with the x's going minus a to a, this one's going to go 0 to a. Whew. Okay, so put that into your magical black box, let it do its thing. And what we end up getting here is 4a over 3 pi. So that's how far we're going to go up to get the center of mass. And looking at it that way, you probably don't have a good understanding of where that's located. But what would help is if we figured out what fraction of a that is. So if you just look at the 4 over 3 pi, that's around 0.42. So this is around 0.42a. So if you were to think of this as 0 to 1, we're only going to go up 0.42. So whoever, Cesar, who said it was slightly towards the bottom, and it is. It's just slightly towards the bottom. It's just under a half, just under halfway there. But it matches what we expected. We figured that it should be a little bit below because of the fact that there's more mass distribution down there. All right, so this probably felt a little bit more like calculus than physics, but this is one of the reasons why we teach you this stuff in calculus, to show you some examples. Also why we have you take calculus before we get to physics, because now finding that center of mass is going to matter. Because let's say we're talking about this shape, this semicircle, maybe we've got some sort of a space probe that's shaped like that, and we want to know what's going on with it. We don't need to worry necessarily now about any kind of a tumble or spin. We can just follow that center of mass. Where that center of mass goes is where the entire thing's going to go. And so we can get away from some of that complexity. And up to this point in physics, we eliminate a lot of that complexity out of necessity, right? When we go no air resistance, or we say strings are massless, or any of the other nonsense that we say. We do that to make the math easier because we can't, there's no other option. But center of mass is making the math easier, and it's totally legit. We're not just hand waving. We're not dumbing it down. There's a lot of work. Like we had to work to find that center of mass, but now that we've got it, we just follow that and we're good to go. All right. So let's take a pause here. I'm going to pause the recording for a second. All right. So now that we're done with chapter 9, let's go ahead and move into chapter 10. We're going to start our conversation on rotation. Up to this point, everything we've talked about has just been things moving linearly, which is great. I mean, we need to know about it, but it's awfully simplistic, because even something as simple as tossing a pen in the air, you see that pen tumble, you see rotation happen. And so we need to take that into account. We need to figure out how that works. Now, obviously, this is going to bring back some trig. So you can tell I'm getting really excited. But we're definitely going to use trig here. And more to the point, we're going to use the part of trig that isn't triangles, right? We're going to use the part that you first learned that had to do with circles and all that, including arc length and angular velocity and all that kind of stuff. So we're going to basically start from scratch. I know that a lot of you know these things already, but this will be good review, get us all on the same page, and we'll start seeing how we treat rotation and how similar it is to linear motion, but also how different it is. You're going to see a lot of parallels, and this is one reason why another reason I like rotation, is that everything that you've learned up to this point has a direct parallel in rotational stuff. It's just, it can be a little bit more complicated because now we have bodies that are rotating. And after we get rotation down, we'll put the two together and we'll talk about things that are rolling. Let's say if you've got a log that's rolling, it's doing both rotation and lateral, linear motion. And we're going to be able to put these things together pretty seamlessly, but we need to have a good foundation. So with that, let's kind of remind you a little bit of stuff you learned in trig, and I'm going to go to the board. All right, so we should be back to the board. Let me get rid of this real quick. But back in trig, and this would have been like day 1. I know that I just taught this on Monday with my trig class this quarter. When we were talking about angles, one of the things we talked a lot about was rotation. And as you guys know, I'm a firm believer that circles and triangles are really just the same thing. But you may remember seeing a picture like this, and we were relating the arc length, the actual distance on the circular path, to the radius of the circle and the angle theta. So does anyone remember what that relationship was? What the formula is?
Between arc length and angle?
Yep, that relates S and theta. It also uses R.
I have no idea.
All right, well, it's a good thing that I'm bringing this back up then.
Yeah.
You know what we're going to do? We're going to derive it real fast. We're going to derive it, and we're going to use proportions. So what we're going to do is we're going to look at arc length, and we're going to compare it to angle. And let's think about what it looks like for just this little piece. The arc length, of course, is S, and the angle is theta. So if we rotate a bit,
I had to piss so bad I went to go I'm
gonna
get into
okay, so if we just look at this, we go a distance of S on our circular path as we go through an angle of theta. Okay, so I just got that ratio right there. If you want, think of this as an orbiting body, right? This is the moon going around the Earth, and we're just looking at how far is the moon traveling through space as it sweeps through a certain angle, right? Okay, so we've got this for our little chunk here. Imagine we did a full circle. If we do a full circle, the total arc length is going to be 2 pi r. It's the circumference of the circle, right? If we look at the moon as it does one complete orbit around the Earth, it's going to travel a distance of 2 pi r, where r is the orbital distance. Well, let's keep going with this ratio. Set up this proportion. We've got the arc length over the angle. What kind of angle do we do if we do one full circle?
360.
Okay, so Max, because this is physics class, I'm going to
Oops.
allow that. This is the one and only time. So remember, in calculus class, we don't touch degrees. In physics class, we do, right? So your one
Yeah.
warning. Yeah, it's all good. It's all good. So obviously, instead of degrees, what is it in radians?
2 pi.
2 pi. There we go. So we put our 2 pi here. Obviously, you can cancel some stuff out. And we get S equals R theta when you're in radians. And this is one of the reasons why we like radians. I say we because I'm trying to force it on you. But that's one of the reasons why I like radians. And that's because it simplifies these formulas. If we had done this in degrees, we could have done it with 360. But then we would have ended up having S is equal to pi over 180 times R theta. And ain't nobody got time for that nonsense. So if we're in radians, we get S equals R theta. All right. So the reason that I even wanted to hint at doing this is because if we're going to start talking about an object as it's moving around in a circle, we need to be able to talk about velocity, accelerations, all that kind of stuff. And that all begins with distance, right? We have to have lengths and times, and this is how we're going to get lengths. These are going to be the lengths, distance traveled by an object. So S equals R theta. So we call this the arc length formula because it's the arc length is R times theta. But notice that it does depend on two things. The radius. If we have a larger circle, if we sweep through the same angle, the arc length will be greater. I mean, I actually have two drawn here, right? The one for where I marked my angle. But notice that the bigger R led to a larger arc length. And it also depends on theta. If we go through a larger theta, we're going to sweep through a longer distance, and that should kind of be obvious as well. I mean, think about a piece of pizza. If that piece of pizza has kind of like a thicker wedge, the crust length is going to be more. So for those of you who like your pizza crust, you want the really wide slices of pizza. But those who like just the toppings, you also want the wide one because you get bigger area. All right, so there's our arc length. Now, let's go to figuring out velocity. So if this is the distance traveled, then the velocity is just going to be that distance over time. So we're going to take that S, R theta, and we're going to divide by time. Now, what I am assuming here is that I've got a constant velocity. If it weren't constant, of course, I would differentiate, and we'll get there in a second. Right. So in a case of constant velocity, we get R theta over T. But I want to rewrite that as R times theta over T. All right. So the reason I did that is I want to look at this guy, theta over T. So if you think about what that means, this is the angle that we're sweeping through, that we're rotating through, and T is time. So this is an angle per time. Well, that's really similar to velocity, right? Because velocity is a distance per time. This is now an angle per time. And so we actually call that a velocity, but we call that angular velocity. So what I have written here, velocity, I'm going to put in parentheses down below. This is really linear because we can also have angular. And angular velocity, we use this curvy W. It's not a W, it's an omega. This is the Greek letter omega. It's the lowercase omega. But that angular velocity, that's our angle over time. So exactly the same idea, except now it's not distance per time, it's angle per time. So you'll hear me say things like, how fast is it rotating? That's finding this angular velocity. What kind of a rotation is it doing per time? And so if our angles are in radians, I want you to notice what happens with this formula for velocity. We end up getting that V is equal to R times omega. So let me write this stuff back up at the top because I know we're getting cluttered. But I want these all together because you're going to start seeing some relationships. All right, now I did all this as constant velocity, but even if it's not constant, we can actually approach it exactly the same way. We'll start with that S equals R theta, but now we're going to differentiate. So if we have S equals R theta, take a d dt of each side. Now I'm going to assume that the radius is constant, that we're traveling just in a circular path. If it's not, we have to use the product rule on this. Since I'm assuming that it is constant radius, I can just pull that R out. So I get ds dt is equal to R times d theta dt. And now these are instantaneous, right? This is an instantaneous rate of change in position, an instantaneous rate of change in your angle. But you already know this is velocity, linear velocity. And so this other one is still angular velocity. And so we get exactly the same place. All right, so angular velocity plays the same role as linear velocity for rotating objects. It's telling us how quickly it's rotating. So think about something that spins, right? Like a Frisbee, a DVD, right? Anything like that. As it's spinning, the speed of its spin, how fast it's rotating, how many RPMs, that's a measure of angular velocity. So imagine something that turns very slowly. Let me bring you to this picture. All right, so I'm gonna have a pen be my rotator because we can kind of see it a little bit better. So I'm gonna rotate it, right? I'm spinning it around the axis that's right in its center. But this is a pretty small omega. It's not spinning very quickly. It's also not constant, but it's a pretty small omega. A fast omega would be something like that, right? If I start rotating it quickly, that's going to have a greater omega. Now you'll also notice that along the way, I went from spinning it, say, one direction clockwise to counterclockwise, except I guess to you guys, it's vice versa. Well, in that case, I've got either positive or negative. Just like with velocities. Velocities are vectors, and so we have left and right. Same thing with omega. Omega positive, omega negative, it's a different way of rotating. But we use the exact same sign convention as we did for angles. So you remember positive angles? Those happen when we go counterclockwise. So positive omega is spinning counterclockwise. Negative omega is clockwise. So I'm going to write that up on the board because that's a really important distinction, and I want to make sure you guys have it. And this is true for angles as well. okay? But I'm going to write it for omega. So if omega is greater than 0, this is counterclockwise. Or if you learned British English, it's anti-clockwise. If omega is less than 0, it's clockwise. So that's nice. It's the same convention as what we're used to with angles, but it's going to matter. It's absolutely going to matter when we go through the kinematics and actually do computations. So remember how velocity is a vector? Well, so is omega. Omega is also a vector, but it's related to velocity through a cross product. Because like when I wrote this right here, this V equals R omega, I really should have been talking about this as the tangential velocity. It was kind of implied by how I drew it that it was velocity along the path of the curve. And so that's tangential velocity. But you know that if you have an object, that you can have velocities that are pointing in multiple directions, right? You can break it into components. And so if you think about something moving around on a circular path, let's give it just some random velocity, okay? So like, let's say that this is V. I can actually break it into components. One that points towards the center, and the other that's tangent to the curve. And so it's this one right here that's the tangential. The other one, we call this radial. Another word that you'll sometimes see other than radial is centripetal. Kind of depends on what we're doing and the context of the problem. But radial, because it's pointing along the radius. Centripetal, that literally means centrally pointing. So it's pointing towards the center of the circle. So I'll use both. Sometimes I'll say radial, sometimes I'll say centripetal. I would say I would try to be consistent, but you and I both know that that won't happen. But when we did this calculation, this V, in terms of the magnitudes, you notice I don't have any vector things on here. That is strictly just magnitudes. That's going to find us our tangential velocity. Something going in circular motion will always have velocity because its path is changing direction. Even if its speed stays the same, remember that vectors is not just magnitude but direction. And so even if we were just going around in a circle, so it was always all tangential, we still have a change in our velocity because our vectors are pointing in different directions, which then means, of course, that there's always acceleration since velocity is changing. All right, well, to get back to my point, when I wrote this V equals R omega, that's really just talking about the magnitude, and specifically the magnitude of the tangential velocity. But there is a vector relationship between these things, and it looks like this. If we go to vectors, we get that V is equal to omega cross R. And this R, it's the same kind of R vector that you're used to, which if we've got an object that's moving in a circle, so here's our center and we're moving in this circle around it, the R vector points from the center to wherever our object is on the circle. Okay, so that's our R. We need to cross that with omega to get V. So let's talk about where V is going to point and how we use that pointing V to tell us what direction omega points. So let's go with moving in a clockwise direction. So I'm going to start with, let's say that V is doing this. Okay, so that's our V. Let me actually write it so it looks like a V to you guys. So that's our V. I'm also going to move my R so that it's over there. Remember that a vector doesn't matter where it is, just matters what direction it's pointing. Okay, so the question is, where's omega? So think about the cross product. Hopefully you remember this. When you cross two vectors, where does the third one show up?
Only one that's learned it, right? You're like the you're I don't know if any of them have learned cross product yet.
All right, that's a good point. Real
I think
quick.
I'm the only one.
So thumbs up, you know about the cross product. Thumbs down, you don't know about it.
Because you learn it at the end.
Thumbs
of-
down.
Yeah, you
All
learn
right,
it.
so
at
Max
the
just
end.
gave me a thumbs down. Jesus is giving me a thumbs up. Evan, Bradley, or no? Cesar.
Yeah,
Oh,
that
okay.
doesn't really sound familiar to me.
Okay.
Yeah,
Well,
me
so I apologize for that. This
It
is
was
one
like
of
when
those
you
cases
found out,
where,
like, ooh, I think I'm like one of the only ones that knows.
well, so look at you, Ian. You got a heads up on everybody. Okay, so let me give you a little bit about the cross product. You know about the dot product, yeah?
Yes.
We're good
That's
with
what I
the,
remember.
with the dot product, and the dot product is really used to like find angles between things. There are certain computations we can do in calculus, like work, right? It's force dotted with displacement and stuff like that. So cross product's another way of multiplying vectors. There are actually three ways to multiply with vectors. There's scalar multiplication. So you take a vector times a number, and all that does is change the length of the vector. It doesn't change the direction, right? It might flip it over if you multiply by a negative, but that's it. The dot product, you multiply two vectors and you get a scalar. You just get a number, right? And that number is used for things like finding the angle in between them, the area between of a triangle that's formed with two sides, or blah, blah, blah. There's lots of stuff. Now, cross product is where you multiply two vectors and you actually get a third vector. You get a third vector. So you'll notice that if you go back and look at your notes or look at the whiteboard, let me just throw. You'll see here when I wrote omega cross r, it gave us another vector. It gave us the vector v. So cross product gives you a vector. All right, now let me get back to how you can tell where this vector is. So when you do the cross product, it turns out that the resulting vector is perpendicular to both of the original two. Okay, so think about two vectors. They're going to be in a plane. You can write them on a piece of paper, right? That third vector has to be perpendicular to both of those, which means it would have to be coming either in or out of that piece of paper. So think about when I write two vectors on the whiteboard, that means the resulting vector is either pointing out of the whiteboard or into the whiteboard. Those are our only options. Okay, so then how do you know which direction it points? Well, this is where we're going to use what we call the right-hand rule. Okay,
Oh, yeah, that sounds familiar.
All right, so we got some light bulbs are turning on. So the right-hand rule, you got to use your right hand. Has to be the right hand or else it's going to get backwards. So I apologize for you lefties. This is no, and don't blame me. This is just how this works. So there are two ways to approach this, and I'll try to demonstrate both of them here with my hands and show you. And then we'll get to the whiteboard and I'll help you see how this works. So one way you can do it, using your index finger, you point your index finger in the direction of the first vector. So like in the equation that we have that we've written out so far, right? I've got V equals R, or sorry, omega cross R. My index finger is going to point in the direction of omega. Okay, so you're going to take that and you're going to point it in the direction of omega, however it has to be. Point that in terms of omega. Okay, then you're going to take your middle finger and you're going to point that in the direction of the second vector in your cross product, which in this case would be the R. Okay, so here are my fingers. Index, pointing finger, that's going to be in the direction of omega. Middle finger is going to be in the direction of R. Okay, so I'm going to manipulate my hand however I have to so that these things are pointing in the right direction. Now, once you get those lined up, what you do is you put your thumb up. Your thumb is going to point in the direction of that resulting vector. Okay, so if these right now were my omega and my R, this is the direction of my V. If for some other reason, okay, so here's my omega, here's my R, I stick out my thumb. Oh, you can't see my thumb. There we go. Okay, so here's my V, here's my R, or sorry, omega, my R. That would be my V. So index finger goes on the first one, middle finger goes on the second one, thumb is the direction of the resulting vector. So that's how you can do it with fingers. This is much more fun when I'm teaching it in class because everybody's flipping me off at some point. It's kind of funny. Now, the other way you can do it, because sometimes it's hard to manipulate your fingers like that, is make a flat palm with your hand. Okay. Again, right hand, right hand. Start by taking your palm and pointing it in the direction of the first one. Okay, so however that has to be, pointed in that direction. Then what you do is you curve your palm towards the second one. So it could curve this way, or I might have to try to curve backwards. And since I can't curve backwards, I got to turn my hand around so that now I can curve that way. And once you do that curl, extend your thumb, and your thumb tells you which direction it points. So let me demonstrate that on the whiteboard with a pair of vectors, and then we'll get back to this question of, for our specific case, how we know where omega points. All right, so I'm going to leave this picture, but I'm going to erase up here and draw some random vectors. All right, so let's say we've got these two vectors, and I'm going to call these two vectors A and B. All right, so can everybody see that? We okay? So we've got A and B. So let's try doing A cross B. So I'm going to do A cross B.
I don't know if it's just me, but the board
white
screen is
screen.
frozen.
Yeah, we're just like stuck on the original whiteboard.
Can you see it now?
Yes.
Are we live? I'm moving my hand here.
Mm-hmm.
Yeah.
Okay.
Yeah, it's working now.
Okay. So we're doing A cross B. So I'm going to take my right hand, and I'll show you the two ways of doing this. So the first, let's do the palm one. So I'm going to take my hand, palm, and I'm going to put it in the direction of A. So I can either do it like this, or I can do it like that. Okay, so I have two options. But what I want to do is I want to have it oriented so that I can curl my fingers towards B. So in this case, I need my hand upright so I can curl towards B. That makes my little fist with the thumbs up. And you notice that the thumb is pointing towards you guys, away from the board. So that tells me that A cross B, that vector, is coming out of the board. How big it is, that's another story. We're just talking about direction. But this one's coming out towards you. So the other way, using the fingers, so index finger, point it in the direction of A. middle finger has to point in the direction of B. I extend my thumb, and notice that my thumb is still coming out towards you guys. So that's the right hand rule. We call it the right hand rule, and that's how you can figure that out. Now, if I had reversed it, let's say we're going to do B cross A. So let me just change this real quick. So we're going to do the same thing. If I was to do it with my palm, so I'm going to line up with B, but I need to curl towards A. So I got to flip my hand around. B, curl towards A. I extend my thumb, and you notice that the thumb is pointing towards the board, which means it'd be pointing backward. Same thing if I do index finger on B, middle finger on A, my thumb has to go towards the whiteboard. All right, so that's how you can actually tell what direction this thing points. Okay, so let's come back to this question of we want V equaling omega cross R. Now, I don't have omega on the board. I only have R and V. But what I do know is that omega has to either come out of the board or go into the board, because it has to be perpendicular to both of these vectors. So basically it means it has to be perpendicular to the plane that holds these vectors. All right, so let's think about our different options. I'm going to start with this being omega coming out of the board. So I'm going to do omega cross R. So if it's coming out of the board, I need my palm like this, and I'm going to rotate towards R. And notice what's happening is that my thumb is pointing upward, but that's backwards. V is supposed to be pointing down right now. So my assumption of having omega upward doesn't work here. So let's think about if omega goes down. Okay, well, I'm still going to put my hand so that it's in the plane of this guy, but now I want to curl towards R, and notice now my thumb is pointing up. So basically, the way that this works is that if we're looking down on this rotation, if V is clockwise, omega is pointing down. If V is counterclockwise, so if it came around this way, remember that one resulted from an omega that was sticking up. So omega either points up or points down. It points up if we're rotating counterclockwise, and it's pointing down if we're rotating clockwise. So let me go ahead and write that down.
Quick question. When we do cross product, does that give us 3 dimensions?
Absolutely. Cross products have to occur in 3 dimensions.
As I was just thinking about it, like we have 2 right now on the paper, which is 2 dimensions, and then we go either in or out with omega. That's
Correct.
3, correct?
Yep.
All right.
Yeah, so for angular stuff, we're going to see that when we treat them as vectors, the rotation vectors either point up or down. And I had this conversation with someone not that long ago. I think it might have been my son. He's a freshman up at UNR, and so he's in this same sequence of physics. And he was asking me, is there actually a physical anything? Let me change cameras here. Is there actually a physical thing that this up or down vector represents. You know, because in a lot of the linear stuff, those vectors do mean something. They represent something. And he didn't like my answer, because my answer was no. No, there's nothing that these actually represent. I mean, they point along the axis of rotation. But in terms of the direction that they point, whether it's up or down, it solely is, we need to have a way of designating whether we're rotating clockwise or counterclockwise. We have two options: yes, no, plus, minus, up, down. And that's where we go to the up and down. As opposed to, like this guy Omega. Omega definitely tells you something, right? Omega is telling you which way it's rotating. Like you can physically see as something's going in a circle, it was here, it's following a curve, omega is pointing in that direction. But, I mean, sorry, V is pointing in that direction, but omega doesn't. So it is kind of weird. We are extending ourselves to the third dimension. That third dimension, it's only used because we need it, but there isn't something physically that it represents. So, but yeah, Bradley, this is going to bring us into the third dimension. But that third dimension doesn't really matter, other than we're using it as a way of distinguishing clockwise versus counterclockwise. And that's going to show up in everything we do with rotation. Everything.
And while we're on this sort of subject, I also had a question. All these vectors represent velocity, correct? Like,
no, not necessarily velocity. Some do. The omegas, those are angular velocity. So they do represent a how quickly is this rotating. The V is a linear velocity, which is velocity like you think about it. But like R is not a velocity. It's
okay.
It's a position vector. It's just we're drawing from the axis of rotation, from the center of the rotation of this object, wherever we're rotating about, to the point. And so it really is just a keeping track of where we are. That's what R is doing. It's just keeping track of the location.
Oh, so it's just like a sort of directional vector or a position vector? Okay.
Yep.
Right,
yeah, it's
cool.
exactly that. It's a position vector. And that position vector is getting crossed with the angular velocity to get our linear velocity.
Okay, that makes sense. Thank you.
All right, you're welcome. Other questions?
So just to make sure, I was having trouble like understanding this, but the whole thing with like omega pointing up and pointing down, that's just to figure out if it's going counterclockwise or clockwise, right? That's all it is?
Correct. All it's telling you is the direction of spin.
Okay,
And
yeah, because I was trying to figure out, I mean, if there was a physical, like, as you were talking about it, I was trying to figure out, like what is that? What does that mean? But now it makes sense that it's just it's kind of like a technique, right? Is that what it is?
kind of.
Right.
It's just a way of making sure that when I'm talking about a rotating object and you're talking about a rotating object and anybody else is talking about it, that we all have the same understanding, same convention. And so that's really what this comes down to, is so that we're all communicating the same language when it comes to rotation. And here's the thing though, I want you to realize that it's all about your own observation. Like, this is relative, because let's say I've got something spinning right in front of me. Let me see if I've got something kind of roundish that doesn't have like fluid in it, if you know what I mean. All right, here we go. So here's a scout patch from my son. Okay, so I'm going to rotate this. So I have a question for you. Is this rotating clockwise or counterclockwise?
To me,
Clockwise.
clockwise.
Okay, so you guys are all good that it's clockwise, right?
Yeah.
Okay, but to me, it is not rotating clockwise. To me, it's rotating counterclockwise.
I
So
see.
I would say that it has a different rotation. So yes, Chase, it definitely depends on your perspective. Now, let's think about where omega is pointing for you guys. So you see it moving clockwise. which means which direction should the vector be pointing?
I guess up, maybe? Is it towards me is up?
So
Or-
towards you would be up.
Yeah.
So clockwise, if we go back and you look at what we were looking
Oh,
at,
down.
clockwise should be down, which according to you guys would mean it's pointing towards me, right?
Yeah.
Okay, so according to your observation, you would say that omega is pointing towards me. Now, remember, I saw it as moving counterclockwise. So I would want to see the vector pointing up. Well, the up to me means towards me. So regardless of our perspective, we still agree, right? You guys all think omega should be pointing towards me because you're seeing a clockwise rotation. I'm seeing counterclockwise rotation, which means I think the vector should be pointing towards me. It's still the same, right? So this is what's actually really beautiful about this. Whether you call it clockwise or counterclockwise, however you decide that you're observing it, whether you're going to call it clockwise or counterclockwise, you know, from how you're seeing it, someone who's seeing it on the other side, they will still agree with you the way that we set up this convention. So that's the other reason that we do it this way. Not only are we all on board with what it means, but we can all agree with what it means. So does that make a little more sense?
Yeah, it does now, yeah.
Feeling a little bit better? Okay, so I know it's weird. It's definitely a trippy thing. We're just gonna have to get used to it. We're gonna have to get used to how this spinning works. So, you know, the whole up and down in terms of the pointing, I think of it as if I'm looking at my piece of paper, right? If I've got this thing rotating on the paper that I'm writing my notes, that means up and down. So maybe it is better towards you, away from you, towards the observation, away, however you want to think about it. But that's what omega is going to tell you. It's basically our way of saying which way is it rotating, because it will matter, right? It obviously will matter when we try to deal with this, which direction it's rotating. Because here's a great example, a real world example. Think about like a baseball. Again, you guys know I've got baseball on the brain and I'll do anything to get it back. But when a pitcher throws the ball, they put rotation on it. That rotation is what makes it move the way they want it to move. If instead of rotating, like let's say clockwise, it rotates counterclockwise, it's going to move completely differently. And that's going to absolutely impact the result of the pitch and then the swing and the game. So how something rotates is just as important as knowing it rotates, especially when we get objects that are not symmetric, that have, you know, weird things to them, like a baseball having ridges. That can definitely make it so that some rotations are not the same clockwise versus counterclockwise in terms of their result. So we just got to pay attention to that. And that's what this cross product nonsense is doing. So again, I apologize that I assumed you guys had seen cross products. I know you're going to learn about that this quarter in calculus for sure. I guess I kind of forgot where we were in the sequence, but we're going to continue to see the cross product because a lot of rotational stuff involves it. The more we do it, the better we're going to feel. And I'll see if I can find some resources on the cross product and put some links up on our Canvas page to get you to some things that might explain it better, some YouTube videos. Also, if you guys find anything like that, and I don't just mean about cross products, if as you're studying, you go somewhere and you find interesting things that help with the concepts that we're talking about, let me know. And I'll be happy to put them on the Canvas page so other people can see it. Or like Ian was saying, go to that virtual math lab and you can share that stuff there too. All right, so angular velocity, just take it for what it is. It's rotation. It's the rotational equivalent of linear velocity, right? It's how fast we're rotating, how quickly the angle is changing. All right, well, this then also brings us to, if we've got a velocity, then we must have some sort of acceleration, right? So let's take a look at angular acceleration. All right, so we've got S equals R theta and V equals R omega. Well, we can also look at angular acceleration, just like we had linear acceleration. And linear acceleration came from linear velocity, which came from linear position. The same sort of thing spills out for these omegas and angular acceleration. So if we go back to kind of definition, omega was d theta dt. It was how quickly the angle is changing with respect to time. All right, now angular acceleration is going to be the derivative of this. So we're going to do a d omega dt, and we use alpha for angular acceleration. So angular acceleration is a measure of how the angular velocity is changing. So think about something that's spinning, bicycle wheel, let's say. If that bicycle wheel starts speeding up, it's undergoing angular acceleration, right? It's rotating at a nice little clip, just same speed, right? So we're going around in a circle. But if we start going faster, I just increased my angular acceleration or angular velocity. So I had a positive angular acceleration. If I start slowing down, I decreased my omega, which means I had negative angular acceleration. So it really is the same kind of idea as linear, right? Positive linear acceleration means our velocity is increasing. Negative linear acceleration meant that our velocity was decreasing. So it plays exactly the same role. So it's the derivative of omega, which means, of course, it's also the second derivative of theta. So if we know how theta is related to time, then what we end up getting is the second derivative of that will give us our angular acceleration. Okay, so let's go back to that clockwise, counterclockwise thing. If alpha increases, or let's just say if alpha is positive, that means our omega is increasing. So let's just think about if we already have positive omega, means that we're rotating counterclockwise. Then what's going to happen is it's just going to keep going counterclockwise, but faster, because we're getting more positive. If our omega is negative, so we're spinning counterclockwise, if alpha is positive, it's going to get less negative. So it's going to slow down until eventually it stops rotating and then starts rotating in a counterclockwise direction. So think of positive alpha is trying to make it more clockwise. It's trying to spin more clockwise, or sorry, counterclockwise. So if it's already spinning counterclockwise, it's going to go faster. If it's spinning clockwise, it's going to stop spinning clockwise and eventually start going counterclockwise. Same thing if alpha is negative, it's just reversed. Now negative alpha is trying to make it go clockwise. So if it already is spinning clockwise, it's going to spin faster. If it's spinning counterclockwise, it's going to slow down until it stops and then start going the other direction. This is exactly the same as linear acceleration, plus and minus. Positive acceleration meant we are going speeding up to the right. If we already were moving right, we keep moving more. If we were moving left, we slow down until eventually we start moving right. Or think about it vertically, like when we toss something in the air, right? We always have negative acceleration is trying to pull us down. Even though we were moving up at first, we slowed down until eventually now we start coming back. So just in your head, the way to deal with this is just to think about it as a rotational exam, same kind of idea as we're either trying to rotate this way or this way. And positive versus negative is associated with one of those, right? So positive is counterclockwise, negative is clockwise.
Quick question.
All right, so I know that's kind of trippy. I'll try to bring some, next time on Friday, I'll try to bring some things that rotate, like pinwheels and stuff like that, that we can better see what's going on. Obviously I don't have anything like that right now, but we'll see if we can get some things that I can show on the screen to help you see a little bit better what's going on. So let me share a little bit more with acceleration, and then I think we're going to call it a day because you guys have been troopers, and I know that this is probably messing with your mind a bit. But I'm going to go back to the board. So I want to come back to this example, or this idea of S being R theta and V being R omega. As I mentioned a little bit ago, this V is really a tangential velocity, so I'm going to put that V sub t, because the velocity itself can be pointing in the other direction. Well, if we want to extend this to acceleration, imagine taking a derivative of this with respect to t. So if I do d dt of the v is equal to d dt of the r omega, again, assuming r is constant, this is going to give me tangential acceleration, because it's telling me how the velocity's acceleration, or the tangential velocity is changing. And on this side, since r is constant, we get r, but then d omega dt is alpha. So check it out. These three all have the exact same structure. The linear bits are all equal to the angular equivalents times r. Okay, so if you know one of them, you know all of them. Okay, but that, at least that's their magnitudes. Because just like velocity doesn't necessarily point only tangentially, same thing with acceleration. And so just like I did when I drew that picture before with velocity, imagine that this is our A. We still will want to break it into bits that are either tangential or radial. Okay, so this guy, the r omega, that's going to tell us the magnitude of the tangential piece. We'd also like to be able to get this one, the radial bit, because the acceleration vector itself right? It's going to be the sum of those two things. So yay, I can find the magnitude of the AT, but I'd really like to be able to find the magnitude of AR. And I don't know if you remember this, or if for sure, I don't know if Kathy actually covered it, but I know it's back in like chapter 3 or 4 when you talk about circular motion. There's a way to calculate the magnitude of the centripetal, the radial acceleration. Anybody remember that? Does that even ring a bell?
Not that I'm aware of.
The centripetal acceleration?
Yep, of the radial. And no is a perfectly fine answer, by the way, if you don't remember.
Yeah, I don't think Kathy taught us that last.
Okay. That's no problem. So it turns out that when you go around in a circle, this radial, the centripetal acceleration, I'm actually going to call it A sub c because that's what I'm used to, centripetal. But the magnitude of AC is actually the magnitude of the velocity squared over the radius. So when you're going in uniform circular motion, A is equal to V squared over R. Okay, so your centripetal acceleration is actually dependent upon your velocity. But let me show you how we can tie this still further together. So we've got A centripetal, so centripetal acceleration is equal to V squared over R. All right, well, V we know is equal to R omega, the tangential part, I should say. So that's going to equal R squared omega squared over R, or R omega squared. So this is the other piece of your acceleration. So on the left, we've got our tangential acceleration is R times alpha, and our centripetal or radial acceleration is equal to R omega squared. So that's the size of these vectors, which means if we want to actually know the magnitude of just A, we can use the Pythagorean theorem, good old A squared plus B squared equals C squared. And so let me just go ahead and finish that thought down here. The magnitude of A, so this is the acceleration period, the entirety of the acceleration. It's the square root of R alpha squared plus R omega squared, which if you do a little simplification on this gets you R times the square root of alpha squared times omega to the fourth. So if we have an object that's spinning, that's moving around in a circular path, you can actually determine the acceleration that's being felt just by looking at the angular quantities. If you know omega, if you know how quickly the angle is changing with time, if you know how the angle's velocity, the angular velocity is changing, that's your alpha, and you know the radius, you know how far away it is. So this, what I've got here in terms of the boxes and this last thing that I computed is really our way of getting out of linear and into radial, or sorry, rotational, or vice versa. This is the link between those two quantities. Okay, so when we start dealing with things that actually have rotation, so we talk about wheels that are spinning, planets that are in orbit, that kind of stuff, we're going to want to tie that rotation back to what we already know. And that's what all of these things are going to do. All right, well, I think I'm going to pause it right here. So let me just pause the recording real quick.